In this section, we will look at the logarithmic functions. A logarithmic function is going to be the inverse to the exponential function, so a lot of the properties that we discussed in the last chapter will carry over. So it's the inverse specifically to the exponential function. And of course, we're going to have to make sure we understand where the bases are and how that affects the computations. So say we want to solve this equation for x. This will begin to give us an intuition behind why these functions are, why they're useful and why they even exist. Well, to solve this equation for x, we could probably do it in our mind by just thinking about the question, the number 2 to what power gives us 8? Well, if you're thinking about that, 2 to the 1 is 2, 2 squared is 4, oh, 2 to the third is equal to 8. So again, this example isn't too hard, but this question does have its limitations. What if we were dealing with fractions or larger numbers, and or maybe we need to figure out a way to deal with irrational numbers like base e, where we need to maybe utilize some computational power like calculators or something to that effect. So we'll come back to this problem once we have these logarithmic functions developed. So here we have some conditions. So the first condition is that x is greater than 0. So that's basically talking about our domain. We have a, again, is going to represent our base. And we have the same condition that it is greater than 0 and it cannot be equal to 1. So we have our logarithmic function given as this, that it is f of x, or in this case y, and it is going to be equal to log base a of x. So a quick thing to note, if you're looking at this, it's very important to notice that that a is lower than the logarithm. It is the base. So it is not in line. When you write it, you want to make sure it is indeed under the log. The x is the input to this function. It's important that you always have it because log base a by itself means nothing. One way you could think about this is if you have a tree. So here we have a tree off to the left, and we have a top. The different parts of this are, well, you have the bottom part, the stump, and this is going to be your base. You have the middle part, which is the actual log, and then you have the top, which is the input to the function, or the x. All three parts are needed for an expression to make sense. What we're going to now work with is just converting it back to its exponential form, and then we can see the relationship between them. So if we want to understand these further, what we can go ahead and do is switch it to its exponential form, and that would be x equals to a to the y. So you can see a switching between the variables that is closest to the base, and that's going to help us switch between them. So let's go ahead and formalize this down below. As mentioned, the first equation is referred to as the logarithmic form. And the second equation, because it has an exponent, is the exponential form. To switch between the two of these, just keep an eye on where the base is. Notice in this one, the base is on the base of an exponent, hence we'll call it an exponential form. Where in the logarithmic form, the base a is on the base of the logs, hence we call it the logarithmic form. And then to figure out what is happening with the other parts of it, take a quick look at the exponent. That exponent, in the first case y, becomes the output of the function, and then the x, which was the closest or the farthest thing away from the base in the exponential form, is now the closest thing to the base in the logarithmic form. We'll now look at these in a few examples. In the first example, we are given the exponential form, hence the exponents. If we want to convert it to the logarithmic form, the first thing to do is recognize the base. In this case, the base is 4. So what I'll do is to switch it, I'm going to go ahead and write my logarithm, so log, and then the base of this is going to be the same as it was in this exponential form. And now what I'm going to do to get the input to the logarithm, and sometimes the input will just be specified with it parentheses, you'll go to the other side of the equation and get the 64. So log base 4 of 64. And then, well, all that leaves is the 3. So we go to the exponent, and that is what the output to the logarithmic function is. So here we have a few more complicated examples, but I'll let the fractions scare you. It's the same process. So again, what is the base here? The base is 1/2. So I'm going to have a log base 1/2. And again, notice how that 1/2 is small at the base of the logarithm. I will then go to the other side to get the 1/16. So 1/16 is the input to this logarithmic function. And then that would be equal to 4. And begin to notice the relationship between the base and the numbers and then the other side, the equal to sign. You can see that 1/2, well, if you just focus on the 2 and the 16, 2 to the 4th is 16. And in the first example, 4 to the 64, well, or 4 to the 3rd is 64. In this last example, we don't have 3 numbers to deal with, but that doesn't mean we can't switch the forms. The base here is again just a, so we have log base a, then the other side 7 is equal to a -2. And now in example 2, we can go ahead and go the other way. Notice that we're given the logarithmic form, and then we have to go and convert it to exponential form. So again, noticing here my base is 3, well, then you would raise that to the number that's on the other side. 3 to the 5th is equal to 243. And again, that should make sense if you were to compute that. 3 to the 5th, 3 times 3 times 3 times 3 times 3 is equal to 243. Here we have a base 2, so we have 2 to the x is equal to 5, using the same process as we did in the first example. And in this last example, everything is symbolic, but that doesn't mean we can't do it. So we have a to the x is equal to n. So again, it's all about that base.